In this video for 3.4, 3.5 part 2, building polynomial functions from their roots, we're going to go over a couple of things. Remember that complex roots always appear in pairs. You can call really any root a complex root. We'll talk about that in a second. In terms of the zeros of multiplicity, if x minus c, which is a factor, occurs in the function m times, then c is a zero of multiplicity m. So my example here, this factor occurs m times, and my m is 4. Therefore, this has a multiplicity of 4. Okay, so let's look down a little bit more. Okay, so we're going to do some factoring first using the GCF. So if I give you this polynomial, I'm not going to give you this picture, but I'm going to talk about this picture in just a second. So if you're given this polynomial and you want to get the factors, what you're going to do first is do greatest common factor factoring. So that means you're going to take out an x squared, and to get this expression back, you need this. Now, when you get to this point, what you want to recognize is that this is hard factoring. So you're going to ask yourself what multiplies to 2 times a negative 1, so that's a negative 2, and adds to negative 1. And the numbers that multiply to a negative 2 and add to a negative 1 are negative 2x and positive 1x. So you're going to expand this trinomial into 4 terms by decomposing the negative x into negative 2x plus x. So now the x squared keeps coming down. Look at your first pair. What do they have in common? They have a 2x. You pull out a 2x, and then to get this first pair back, you're going to multiply by x minus 1. Bring this operation down, make this match over here, and then say to yourself, if I need to get a positive x minus 1 back, and I'm going to multiply it by x minus 1, I need a 1 to get placed here. So my factors from the hard factoring are going to be 2x plus 1 and x minus 1. Now, set each of your factors equal to 0 and solve. Okay, this has an x in it. It is a factor. So x squared equals 0, so x is going to equal 0. Now, because you have a multiplicity of 2, I'm going to write it down twice. So I have x equals 0 and another x equals 0. That's why right here I have a little boomerang. It kind of does a U-turn and comes back around. Then I have x equals negative 1/2 from here. That's right here. It goes right through. And that's how I have x equals 1 right here. And that is x equals 1 right there. So I have 4 roots because the degree is 4. And I can see my 4 roots right here. Same idea here. This is an easy factoring. Use your GCF of x. Factor that out from your initial polynomial function. Then you're going to factor what's in parentheses. You can get x plus 1 and x plus 1. That means your zeros are, this is a factor, x equals 0. That's your first root. X plus 1 equals negative 1 is your next one, and here's the second one, at x equals negative 1. So you had a degree of 3, and you have 3 roots right there. Okay, continuing down. This you need to know. If you have a multiplicity of 1, your function is going to pass right through the x-axis. Okay, that's a multiplicity of 1. If the multiplicity is even, it's going to do a U-turn right at the x-axis. If your multiplicity is odd but greater than 1, it's going to do that little curvy traffic circle type thing. It'll pass through the x-axis, but it takes a little lag time. Okay, so you want to definitely know that. Okay, moving on. Here's another kind of factoring by grouping. You already have 4 terms. Look at the first pair. What do they have in common? X squared. X plus 5 is what comes next. Bring down this operation. Look at your second pair. Knowing that this has to be an x plus 5 to match this, what could you put here? And the answer is a 4. What are your factors? X plus 5 and x squared right here minus right here 4. Okay? This is not completely factored because it's not a linear term yet. Break up this difference of perfect squares into x plus 2, x minus 2. This is a cubic. Set your factors equal to 0, and you get the 3 roots. Here you have a cubic, but look, it's not set equal to 0 yet. Do that first. Now you have 4 terms. Handle it the exact same way you just handled the previous problem in number 3, and you should get 3 roots, and they're listed below in the box. Okay, so this might be the only thing that's going to be somewhat new. This is factoring by variable substitution. This you do when you see the famous 4-2 combination. The only powers you have of x are 4 and 2. That happens both places. So you're going to do variable substitution. I said, wouldn't it be nice if this was squared and this was just plain old x? Because then I know how to factor. So substitute a z in for every x squared. I can now rewrite this equation as z squared minus 10z plus 24. See how I'm getting it from this equation right here? This is easy factoring. Z minus 6 times z minus 4. At this point, recognize that you don't really have z, you really have x squared. Make that substitution back. This is a difference of perfect squares. You get x plus 2, x minus 2. So what happens right here when you have x squared minus 6, set this equal to 0, and you will get x equals plus and minus radical 6. Here are your 4 roots. Let's do the same thing over here. Here's your famous 4-2 combo. Substitute z for x squared. Rewrite your initial formula or your initial polynomial in this way. Then you're going to ask yourself, because this is hard factoring, what multiplies to negative 6 and adds to negative 1. And your answer is negative 3 and positive 2, both with z's attached. Factor the first pair. Actually, I take that back. What I did now, I substituted in x to the 4th for z squared, x squared for z, x squared for z, and I have my 3. Factor the first pair, I get x squared times 2x minus 3. Bring down this sign, and then match up the 2x squared minus 3. You need a 1 in front here. Your 2 factors will be x squared plus 1 and 2x minus 3. Look what's going to happen here. This is x squared equals plus and minus I. So go over that carefully, make sure you're getting that. And here comes x squared equals 3 over 2. Make sure that you're getting x equals plus and minus radical 3 over 2. Okay, so this last piece is finding zeros using synthetic division. So you've used synthetic division to find the quotients, but we never got to find the zeros. So we're going to give you an initial root. Here's your initial root. You always divide by the root. 3, 2, 1, blast off. You have all the coefficients you need. You should understand how to do synthetic division. Now the difference is, take your answer, your quotient, which is going to be x squared minus 6x plus 5, and factor that. This was your initial factor. You got that from your initial root. When you factor this, you end up getting x minus 5 and x minus 1. Those are factors. Here are your roots. Okay, same thing for this example. I'm looking here, 3, 2, 1, blast off, and constant. I have everything I need. Excuse me. Here's your initial root. This is on the outside. When you do synthetic division, you should get this. Since your original polynomial was a quartic, your quotient is a cubic, which you can then factor by grouping, which I've done here. Here are all your factors. These are the two you got from grouping. Here's the one that was given you up here when they gave you an initial root. Your factors are going to be x equals -1, x equals plus and minus radical 5, and x equals 1/3. That is 1, 2, 3, 4 factors, which makes sense because it was a quartic. Okay, there are the answers to the problems I've just done. You should be able to do the homework once you've gone over this video.